Hello everyone, Charu from this side, Assistant Professor from IIMT College of Management from BC Department. Today I'm going to give you a session on Intel 8085 microprocessor. So let's talk about the topic. First of all, I'll give you some introduction of microprocessor. Basically, microprocessor follows a sequence that is fetch, decode, and then execute. Computer Central Processing Unit, basically built on a single integrated circuit that is called ICs, is called microprocessor. A digital computer with one microprocessor which acts as a CPU is called microcomputer. It is a programmable, multi-purpose, clock-driven, register-based electronic device that treats binary instructions from a storage device called memory, accepts binary data as input and process data according to those instructions and provide results as output. Basically, microprocessor contains millions of tiny components like transistors, registers, and diodes, and that will work together to complete a sequence or decode our instructions. So let's talk about the inventions of microprocessor. The microprocessor was first introduced in 1971 by Intel corporations called Intel 4001. Basically, that was the first time when a microprocessor was manufactured on a single chip. The processor was capable of performing arithmetic logical operations like addition, subtraction, etc. If we talk about the microprocessor, basically a microprocessor takes a bunch of instructions in machine language and executes them, telling the processor what it has to do. Microprocessor performs three basic things while executing the instructions. It performs some basic operations like addition, subtraction, multiplication, division, and some logical operation using its ALU unit. And then the microprocessor also perform operations on floating point numbers also. And basically, microprocessors can move from one location to another, and it has a program counter register that stores the data and stores the address of the next instructions based on the value of the program counter. Microprocessor jump from one location to another and takes decision because program counter will acquire the address of the data. Let's talk about and let's discuss the block diagram of microprocessor. A microprocessor basically built up for ALU control unit registers array. The ALU deals with the input device or memory for receiving data. The control unit takes care of the instructions and the structures. Registers are identifies and save the registers like B, C, and accumulator. We have some basic microprocessor terms. Whenever we go for the 8085, we have always learn these terms like we have instruction per cycle. Instruction per cycle is a way to measure CPU's instruction speed in a single clock. Let's talk about the instruction set. Basically, instruction sets command that a processor understand to work between hardware and the software. And also we have some bus. That bus is a conductors for data transmission, information control, and task addresses in a microprocessor. They are of three types. That is, we have data bus, address bus, and control bus. And we have word length. Basically, word length refers to the number of bits processed at a time. Also, we have clock speed and clock rate to ability of microprocessor to perform tasks in seconds. Next, we have bandwidth. Bandwidth basically refers to the total bits in a single instructions. And then we have data types. Data type microprocessor supports like binary, S type, etc. And then we have single instruction, multiple data. We also have pin grid array, and we have floating point unit, as well as we have arithmetic and logical unit, and we also have multimedia extension and memory management unit. Okay, so basically we have to focus all these terms before learning about 8085 microprocessor. Let's just introduction of microprocessor. Basically, Intel 805 is an 8-bit NMOS microprocessor designed by Intel in 1977. The microprocessor exhibits some unique characteristics, and it is the reason it still holds popularity among the microprocessors because today's era, whenever we adopt all the microprocessor, we have latest technologies. 8085 is the first one which we have to adopt basically. So the first commercially successful microprocessor was by Intel, and some of the architectural drawbacks associated with the 8080 was also eliminated by 8085. And we have some configuration in 8085. That is, it has 8-bit data bus and it has 16-bit address bus, which can address up to 64 KB. And we have a 16-bit program counter, a 16-bit stack pointer, or a 8-bit registers arranged in a field that is BC, DE, HL. On all these registers work in the pairs. In 805, we required 5-volt supply to operate a 3.2 megahertz single phase clock. Basically, Intel 8085 is used in mobile phones, microwave ovens, washing machine, etc. Let's talk about the pin diagram. In 8085, we also called as a 40 pin diagram because in 8085 have 40 pins. Let's talk about address bus. We have A8 to A15 address buses pin, and also we have AD0 to AD7 address bus, and these pins combine to 16 pins. And if we talk about the A0 to A15, it will combine and it will be combined and by using the MUX technology to reduce the pin. We also have some timing and control signals that we'll discuss in the later section. And also we have some interrupts. Basically, whenever we deal with the microprocessor and we process some instructions, sometimes we have some interrupts available. And we discuss about all the interrupts in the later section. Also, we have some special or serial IO, that is serial input and serial output. Then we have crystal impacts inputs, that is X1 and X2. The 8085 has extension support in new interrupts while with the 3 maskable interrupt, that RST 7.5, RST 6.5, RST 5.5, and 1 non-maskable interrupt, that is trap. And trap has the most priority among all those interrupts. And 1 externally serviced interrupts, that is IIMT. And some have prerequisite to know the 805. These are the bit, word, memory word, bus, system bus, and addresses. Basically, we talk about the 8-bit. Bit is a single bit binary digit, that is 0 or 1. And then we have word. A word refers to the basic data size or a bit size that can process by the arithmetic and the logic unit of the processor. A 16-bit binary number is called a word in 16-bit processor. We have a memory word. The number of the bits stored in a register or memory element is called memory word. And we have bus. A bus is a group of wires, or you can say lines, that carry similar information. System bus is a group of wires that used for communication between the microprocessor and the peripherals. And we have address bus. Address bus basically carries the address, a unique binary pattern used to identify memory location on IO ports. Here we discuss about the data bus. Basically, data bus transfers data between memory and the processor or IO devices and the processor. Okay, and then we have control bus. Control bus carries control signals, which consist of signals for selecting memory or IO devices from given address and directions of data transfer, synchronization of data transfer in case of slow devices. Okay. Here is a complete block diagram of Intel 8085. Let's talk about one by one. We have, first of all, let's discuss about the address bus and the data bus. And address bus and data bus have combined. Let's talk about some, whenever we have some signals, input and output. When high, then data and the address basically combines with the both, and this passes the data and the addresses to the microprocessor. Okay, and here is some sort of registers available here. Basically, it will combine the pairs. That is B, C, D, E, H, L, and all these are the your common, or you can say general purpose register, and this all combined with the 8 bits. We also have some other register, that is W and Z, and that is for the personal use for the Intel 805. And we cannot access all the registers, that is W and Z. We cannot access these registers because this is only for prior only to the Intel 805. Okay, and also we have accumulator, and then we have temporal register, flag flip-flops, arithmetic logic, instructions registers. Also, we have instruction and decoder and machine cycle encoding. We have a timing control. Okay, let's talk about some reset in and reset out. Like sometimes a microprocessor need to reset itself. So when I want to reset in, like then we just pass it, it will pass the low signal and then it will reset, and then we, if we want to again reset out, then we can reset out from this side. Okay, and also I have also we also discuss about that power supply. It microprocessor use a 5-volt power supply, and here is the interrupt control. And I also suggest told you that the trap is the highest priority in the interrupt control. Okay, and then we also have a serial IO control, that is serial input and serial output. Okay, let's talk about some main sections. First of all, arithmetic logical unit, timing and control unit, and registers. Basically, ALU performs some numerical and logical operations. ALU performs like arithmetic and logical operation, and all of you know about all the operations done by the ALU. Okay. Basically, also ALU includes some accumulator, temporary registers, and the arithmetic and the logic. So in the flags, it always stores the results of operations in the accumulator. The accumulator registers will always store the results of any instruction or any operations. Timing and control unit is the section of the CPU, and it is used to generate timing and control signal which are necessary for the execution of instructions. Let's basically the timing and control unit is used to control data flow between CPU and the peripherals, that is your memory. Okay, it is also used to provide status control and the timing signals which are required for the operations of memory and IO devices. Like timing in the control unit is used to control an entire operation of microprocessor and peripherals that is connected to it. And thus we can see that the control unit of the CPU acts as a brain of the computer system. We have some registers that basically registers are used for temporary storage, because whenever we want to instruct the computer or instruct the processor where the data will go, all the data will hold, or all the data will store in the register. Basically, registers are the combinations of flip-flops, okay, and that will use for temporary storage and manipulation of data and instructions by the microprocessor. The data will remain in the registers till they are sent to the IO devices or memory. Basically, 8085 have some general purpose register, some special purpose register. In the general purpose register, we have a B, C, D, E, H, and L. On all those registers are of 16 bits, and these will combine in the pairs. And we also have an accumulator, and also define that accumulator will always hold the results of the instructions. Okay. And we have some special purpose register, that is SPR, that is for user accessible. And in SPR, we have accumulator that will hold the results of the instruction. And then we have program counter. Basically, program counter is the most important registers in 8085. Next, we have stack pointer. Then we have flag registers. Flag registers basically define whenever we have some signs and then other type of instructions available. We have other user non-accessible, that is instructions registers, temporary register, increment and decrement, and address range. Okay. Let's talk about the instructions registers. Like an 8085 microprocessor had the following list, that is one 8-bits accumulator, that is register A, and then general purpose register of 8 bits. These are B, C, D, E, H, and L, and all the register will work in a pair. One 16-bit stack pointer and one 16-bit program counter, instruction register, and temporary registers. In addition of the above mentioned register of the 8085 contains set of 5 flip-flop which serves as a flag, or you can say status flag. A flag is a flip-flop which indicates some condition that arises after the execution of an arithmetic logical instructions. In addition to the above mentioned register, the 8085 microprocessor contains set of 5 flip-flop which serves as a flag, or you can say status flag. A flip-flop is a flip-flop which indicates some conditions which arise after the execution of an arithmetic and logical instruction. Let's talk about the accumulator. The accumulator is an 8-bit register associated with the ALU, and the register A is an accumulator in the 8085. It is used to hold one of the operands of an arithmetic and logical operation. The final results of an arithmetic logical operation is also placed in the accumulator. Next, we have general purpose register. The 8085 microprocessor contains 6 8-bit general purpose register that B, D, C, E, H, and L registers. To hold the data of 16-bit, a combination of two 8-bit registers can employ it, and these are called register pair. The valid register pairs in 8085 are D, E, B, C, H, L, and HLPO is used to act as a memory pointer. Next, we have a program counter. Basically, program counter is a 16-bit special purpose register. It is used to hold the address of the memory of the next instruction. Whenever we want to deal with the data, all the data will occupy on some memory, and the program counter will directly jump to the address of the actual data. So program counter is the most important registers in the 8085. Basically, it keeps track of the instruction of a program while they are being executed. The microprocessor increments the content of the next program counter during the execution of an instruction, so that at the end of the execution of an instruction, it points to the next instruction's address in the program. Next, to talk about the stack pointer. Basically, stack pointer is a 16-bit special function register used as a memory pointer. A stack is nothing but a portion of RAM. In the stack, the contents of only those registers are saved which are needed in the later part of a program. The stack pointer controls the addressing of the stack. The stack pointer contains the address of the top element of data stored in the stack. As we have instruction register, this is the format of the instruction register. We have addressing mode, opcode, and the operand. Okay, and the instruction registers hold the opcode, that is operation code or instruction code of the instruction which is being decoded and executed. Okay. Next, we have temporary register. In a 8-bit register associated with the ALU, it holds the data during the arithmetic logical operation. It is used by the microprocessor. It is not accessible to the programmer. Okay. We have also flag. In the 8085 contain, we have 5 flip-flops to serve the status flag. Like we have carry flag, then parity flag, auxiliary carry flag, zero flag, sign flag. Okay, and these are the most important flag registers in 8085. Like, let's talk about the bus interface of 8085. As you see in the diagram, we have address bus, we have control bus, address in the data bus. Okay, and these bus will combine and this will use to passes the address and the data to the CPU. Okay. Next, to talk about the data and the address bus. The entire 8085 is an 8-bit microprocessor. Its data bus is an 8-bit byte, and therefore 8-bit of data can be transmitted in the parallel from or to the microprocessor. The entire 805 requires an address bus of 16-bit byte as the memory address are of 16 bits. The 8 most significant bits of the addresses are transmitted by the address bus, that is A8 to A15. And the 8 least significant bits of the addresses are transmitted by the data or address bus, that is AD bus, pins AD0 to AD7. Okay. And let's talk about the control and the status signal. So we have ALE, that is address latch enable signal. ALE goes high during first clock of the cycle of the machine cycle and enables the low rate bit of the address to be latched either in the memory or external latch. Okay, IO or AM output, it is a status signal which distinguishes whether the address of the memory or the IO devices S not and S was, that is output. These are the status signals sent by the microprocessor, distinguishes the various type of the operations given the chiplet. Okay. Then we have RD for signal to control read operations, WR signal to control write operation, and ready, that is used by the microprocessor to sense whether a peripheral, that is your input output unit, is ready to transfer data or not. If ready is high, the peripheral is ready. If it is low, the microprocessor waits till it goes to high. Then let's talk about the interrupts. The interrupts are the signals sent to the microprocessor to pause and attend the request sent by the external device. In other words, externals are the external events that occur in real time to seek the processor response. Like we have this diagram will instruct that the interrupts. Okay. Let's talk about some interrupts. We have hold, and then we have hold acknowledgement. Okay, the hold indicates that another device is requesting for the use of address and the data bus, and hold acknowledge is a signal that will indicate that hold request has been received. After the removal of this request, the hold acknowledgement goes low. Next, we have interrupt request signal, that is it has the lowest priority. The interrupt request signal is enabled or disabled by the software. Next, we have interrupt acknowledgement sent by the microprocessor after interrupt acknowledgement is received. Next, we have RST 5.5, 6.5, 7.5, and the trap in. These all are interrupts. When any interrupt is recognized, the next instruction is executed from the fixed location in the memory as given below. Okay, RST 7.5 and RST 6.5, RST 5.5 are the restart interrupts which cause internal restart to be automatically inserted. And the trap has the highest priority among the interrupts. Okay, and these are the order of the priority. Okay, and then we have reset signal, that is reset in and reset out. A reset in reset the program counter to 0, and it also reset interrupts enable and hold acknowledge flip-flops. The CPU is held in reset condition till reset is not applied. And then we have reset out. Reset out indicates that the CPU is being reset. Then we have clock signals, X1, X2. X1, X2 are the terminals to be connected to the external crystal oscillator, which drives an internal circuitry of the microprocessor. It is used to produce a suitable clock for the operations of the microprocessor. Then we have clock. Basically, clock is a clock output for the user, which can be used for other digital ICs and use frequencies same as which processor operates. Let's talk about the serial IO signal. Then we have a serial input that the data on this line is loaded into the 7th bit of the accumulator when RAM instruction is executed. Then we have serial output. 7th bit of the accumulator is output on serial output line when SIM instruction is executed. Then we have power supply. Already we discussed about that. With that 805 needs 5-volt supply. Also we have VSA, that is for ground reference. Okay. 805 instruction of a computer is a command given to the computer to perform a specified operations on given data. Some instruction of Intel 805 microprocessor MOV, that is for move, MVI, load, STA, address, subtraction, RAL, INR, MVI, and etc. So opcode and operands, each instruction contains two parts, that is opcode and operand. The first part of the instruction which is specify the task to be performed by the computer is called opcode, and the second part of the instruction is the data to be operated on is called operand. The operand given in the instruction may be various from such as 8-bit or 16-bit. 8-bit or 16-bit addresses internal register, registers, or memory location. Let's talk about the instructions word side. The digital computer understands instructions written in binary code. The binary code of all instructions are not of the same RAM. According to the word side, Intel 805 instructions are classified into the following 3 types. That is 1-byte instructions, 2-byte instructions, 3-byte instructions. Okay, let's I have some example over here. Let's discuss about one. So let's when first of all we have to move A comma B, then this will move the content of the register B to the register A. Then add B, add the content of the register B to the content of the accumulator, because accumulator will hold the results. All the above 2 examples are only by 1 byte long, and all 1 byte instructions contain information regarding operands and operand itself. Then we have 2-byte instruction. In the 2-byte instruction, the first byte of the instruction is opcode, and the second byte is either data or the address. Example is MVI B, 05. Then 05 move to the register B. Okay, and then 0605. The MVI B, 05 is then the code form. Next, the first byte of 06 is the opcode for MVI B, and the second byte 05 is the data which is to be moved to the register B. Then we have 3-byte instruction. The first byte of the instruction is its opcode, and the second and the third byte are either 16-bit data or 16-bit address. Let's talk about example. Then we have LXIH, 2400H, then load HLPO with the 2400H, and then 21,00,24, then LXIH, then 2400H in the code form. The first byte 21, is the opcode for the instruction LXHI. The second 00 is 8 LSBs of the data 2400H, which is loaded into register L. The third byte 24 is 8 MSBs of the data, which is loaded into the register X. And here LSB and the MSB is the lowest significant data and the most significant byte. Next, we have instruction cycle. The time required to fetch an instruction and necessary data from memory and to execute it is called instruction cycle, or total time required to execute an instructions given by. Okay. First of all, we fetch the next instructions, then decode the instruction and execute the instruction. Here is the example of a microprocessor 8085. First of all, just like we have to write an 8085 assembly program for multiplying two 8-bit numbers. First of all, we just MVI A, 00, that means load immediate data into the accumulator. Then MVI B, 02, that is load immediate data into register B. Then MVI C, 04, that means load immediate data into register C. And then loop, that means add B, add the content of to the accumulator, then DCRC, that will decrement the content by register C by 1. Then JNZ loop, then STA 1000H, that will store the content of the accumulator in the memory location 1000H, and then HLD, that means halt. Thank you. I hope this session will resolve all the issues regarding the 805 microprocessor. Thank you.